Hello everyone, my name is Guillaume Munch-McElhenney from the Galinet team at Inoria, and I am here to present the state of programming with asynchronous exceptions in OCaml, also called interrupts in the terminology of standard ML. They are exceptions that are raised to preemptively cancel a computation under various circumstances, and so they are challenging to reason about because they can arise almost anywhere in the program. In this talk, I will first present you memprof limits, which is a library that implements global memory limits, allocation limits, and thread cancellation for OCaml 4.12. These are new features thanks to the new StatMemProf memory profiler. Then I will talk about reasoning about programs that use asynchronous exceptions. How can we recover from an exception arising at a random place? The thesis of this talk is that ML exceptions are an unstructured facility from which we can carve two distinct reasonable programming structures. This is inspired by the story of Ross error handling. If you do not care or do not use asynchronous exceptions, you can replace it with truly unexpected condition or even bug, which will give you a non-defensive exception handling model. In other words, how confident are you that all the exceptions in your program are properly handled? First, what is memprof limits? Consider two facts. The first one is that in OCaml you can interrupt a computation by raising an exception directly from an asynchronous callback. This is what happens when you press Ctrl+C in the top level. An exception is raised directly from the signal handler for Ctrl+C. Consider also that the new StatMemProf memory profiler comes with new asynchronous callbacks, and they have very interesting properties about when they are called. For each allocated word, it runs a callback with a certain probability. In our case, we will take 10 to the minus 4. Memprof limits represent new things we can do by combining the two ideas. I had several motivations for writing memprof limits and for giving this talk. The first one is that memprof limits implements features that are not standard in Proof Assistant. My colleagues in the Galinet team implement the Coq Proof Assistant. But the Coq Proof Assistant behaves badly in out-of-memory situations. But we know that it is possible to interrupt a computation and fail gracefully when a user-defined memory limit has been reached. This feature is now compatible with threads and with safe resource management. The Coq Proof Assistant also provides a timeout for computation based on wall clock time, and it has to warn users that it is non-portable. But we know that it is possible to have a portable and reliable timeout by simply counting how many words are allocated. Memprof limits gives you probabilistic allocation limits for this purpose. So it is now possible to port these two standard features to the Coq Proof Assistant. The second motivation is that the out-of-memory exception is not reliable in OCaml. The garbage collector can decide to stop the program if it fails to allocate memory. In addition, many places in the OCaml runtime are not resource safe when out-of-memory arises. Both issues would be very complicated to fix. So OCaml needs a better model for out-of-memory situations based on the assumption that small allocations do not fail. Instead, we can propose to use a proper asynchronous exception for small allocations. For instance, a global memory limit as proposed by memprof limit. Then, out-of-memory becomes predictable. It becomes a synchronous exception that only arises for large allocations that are either explicit or implicit. The first motivation is understanding exception safety and resource safety and their interaction. Multicore OCaml will introduce a new primitive resource, fibers. Multicore OCaml has a resource safety model based on cleaning up resources when an exception arises and triggering the cleanup of resources contained in a fiber by resuming it with an exception. The multicore OCaml designer pointed the well-known difficulties this poses with asynchronous exceptions arising at random places. So it is important to understand how one can program with asynchronous exceptions, including in the presence of first-class resources, in order to make informed decisions in the language evolution. More generally, we would like to promote a non-defensive exception safety model. I will now show you a quick tour of memprof limits. Memprof limits is available on OPAM for OCaml 4.12. I will set up an OCaml top level by running memprof limits, which will in turn run the memprof engine. The first example is global memory limit. They interrupt tasks when the major heap reaches a certain size. You can then attempt to recover by freeing some memory, or you can simply cleanly terminate your program. We first define a task, which will be a memory-heavy function that allocates 2.2 gigabytes with 100 million cells in a list. We then define a monitor, which is the function responsible for running the task. We call limit global memory, and this returns either OK if no limit was encountered, or error if the limit was reached. In that case, we attempt to free memory by calling gc.compact. The whole function runs under a global memory limit of 1 gigabyte. It returns out of memory. The second example is with allocation limits. They interrupt tasks after it has allocated more than some limit. This counts allocations, but not the allocation. So it is sometimes considered a better measure of fuel than counting the whole clock time, because you want sometimes that it is reproducible and portable. The unit we count is 1 kiloword. That means roughly 7.8 kilobytes on 64 bits computers. The task will now allocate roughly 100 million cells, but it will do it piecewise by throwing away 1000 cells every time it has allocated 1000 cells. The monitor will set a limit of 500 megawords. Our function allocated 300 megawords. It will call the function limit allocation, and it will return the estimated allocation on success, or it will say that the program was interrupted with out of fuel in case of error. We have a success. It has estimated that 298 million words were allocated. We can run it again and obtain a different estimation. Memprof limits is provided with a statistical analysis that tells you that the estimation of allocated words is pretty accurate. The main difficulty with interrupts is not so much managing to raise an exception in order to stop a computation, as it is to being able to reason about the state of the program once this exception has been caught. This can already be seen in the implementation of memprof limits itself. Memprof limits manages an arbitrary number of limits for an arbitrary number of threads, and it uses a shared global state to do so. If an interrupt occurs while this state is being updated, it would get corrupted. Memprof limits comes with tools to reason about the consistency of state. The idea is that we can skip a check for limits if it happens in the wrong place. Indeed, another memprof callback will happen soon enough. This capability, which is necessary for the implementation of memprof limits, is provided to all users of memprof limits in order to reason about the consistency of state. This comes notably in the form of a resource management combinator called with-resource. With-resource lets you pair the acquisition of a resource with its release. It works as follows. Acquire is called, and if it is successful, then scope is called. In turn, whether scope succeeds or whether it fails, then release is called. It is guaranteed that release is called if and only if acquisition succeeded. In addition, it is guaranteed that during the acquisition and during the release, no interrupt can arise from memprof limits. I want you to think of resource management not simply as something to manage the opening and the closing of files coming from the OS, but as a general technique to mutate and reason about the global state in transaction style. I must mention the known limitations of with-resource in terms of expressiveness. This is due to its well-scoped nature. It is not the ultimate solution. Nevertheless, this is the first time that something like this is made possible in OCaml. I now want to recap why all this is new in OCaml and why StatMemProf is important in the implementation. The first reason is efficiency. We want to perform a check both often enough and rarely enough so that performance is not affected. The second reason is the compatibility with threads. The probability of performing a check is proportional to a thread's allocation rate. The threads that allocate the most are also the ones you are more likely to want to interrupt. In fact, we can reason that there is less than 10 to the minus 50 chance of not being interrupted after allocating 8.8 megabytes in excess. The third reason is masking. We want to be able to skip some of the events in case they happen while we are updating the global state. This is possible because we perform the check often enough. In fact, we are more precise. We know that thanks to the independence of the event, this does not affect the statistical reasoning. The fourth reason is that it lets us approximate the number of allocation for any thread. This reminds the similarity between resource limits and memory profiling noticed by Young and Maziar. In fact, this might let us in the future implement local memory limits, that is, interrupting a task according to an estimation of the memory it currently retains. I now want to talk in more details of the reasoning about interrupts. The documentation of memprof limits provide a detailed guide to reason about recovering from interrupts. I believe this will interest you because I think this is the first time this story is told to the OCaml community. There are three principles to follow. The first one, do not pattern match on the interrupts. In OCaml, you cannot rely on the fact that the interrupt you raise is the exception that is going to be caught at the place you want to handle the interrupt. The exception could have been caught in the meanwhile and transformed or dropped and replaced by another exception. Memprof limits handles this for you because it will remember whether a task has been interrupted due to a limit. The second principle, re-raise interrupts promptly. Both the Isabelle and Coq proof assistants have found necessary to issue guidelines to treat interrupts specially and re-raise them promptly. Similarly, treat bases option.toy with, which converts an arbitrary exception into data, as an anti-pattern. Memprof limits will help once again because it will enforce the discipline by re-raising the interrupt soon after if you drop it by accident. The third principle, ensure isolation of state at handling boundary. The task to be interrupted must not share state with the outside world unless the state is protected by an interrupt-safe abstraction. Next, I will give examples. My first example of an interrupt-safe abstraction is inspired by poisoning in Rust. Whenever you share state and protect it with a mutex, you record alongside the mutex in which condition the mutex has been released. If the mutex has been released due to an interrupt being raised, then you remember that the state might be corrupted. memProfLimits lets you implement this. It provides you with a predicate to test whether the task is currently being interrupted. Then, you can define acquisition and release function that perform the check and that record the condition. This pattern is used to communicate the interruption, and a similar pattern has been used in the Coq Proof Assistant. Next, instead of invalidating the state, we could simply remember the old value and, in case of an interruption, replace the new value by the old value, which is guaranteed to be valid. To summarize, the reasoning about interrupts involves a task to be interrupted and a monitor which will isolate the task. In order to program the task, there is no need to reason about where the asynchronous exceptions occur. One must only strive to clean up and to fail fast in the event of a failure. The monitor must make sure not to share state with the task unless write access to the state is protected under an interrupt-safe resource abstraction. Now, while researching this subject, I realized that finding a meaningful design for interrupts is an open question since SML. The situation with memProfLimits is improved, but it is far from perfect. I propose to go back to the principles of structured programming. As you already know, correctness should follow from the structure of the program. In turn, the structures provided by the programming language should facilitate the patterns of reasoning about the program. OCaml violated this principle. The reasoning about resource safety is currently incompatible with the presence of interrupts. There is a large body of programs and libraries that rely on resource safety and that is currently incompatible with interrupts. When you want to use a library with OCaml, you have to pay attention in which incompatible dialect it is currently written in. Also, ML exceptions try to do two things at once and do it badly. In OCaml, you have catchable exceptions, which include recoverable error codes, jumps for control flow, sometimes exceptions that are a mix between the two. They essentially behave like a result, but more efficient and less typed. Then you have serious exceptions. They include interrupts and bugs. You cannot cache them in the same way. A priori, you do not necessarily want to recover, but you want to clean up and fail gracefully. This is the original meaning of the word exception. This is a story told many times over. The terminology recoverable and serious implies a value judgment. I prefer to distinguish them by how they differ in reasoning. The immediate caller is responsible for recovering or deciding to propagate the exception in the first case. Whereas in the second case, the immediate caller is not involved in the reasoning. Whoever wants to handle the exception ultimately is responsible for making sure that the consequences of the failure remains contained. According to structured programming, they should be offered via two different programming structures, tailored to each reasoning pattern. In the first case, checked exception should give you the best of both worlds between the result type and catchable exceptions. In the second case, we have to devise what would be a design for panics in ML. So what could be a solution? Remember that two of the issues we had to do with misuses of the catch-all exception handler. The proposal is to ban the catch-all exception handler. For backwards compatibility in OCaml, this probably means introducing a class of exceptions which is not caught by catch-all handler. Just like the goto was replaced by more sensible control structures, we will have to replace the catch-all handler by well-behaved and suitable substitutes. There are various valid uses of the catch-all handler. One is promoting a checked exception into a panic, which is better done explicitly. The second is to clean up before raising. So the whole proposal hinges on the possibility of an expressive enough resource management facility. I believe that once we have identified what programming structures and informal reasoning patterns we need to support, this will inspire interesting directions for more formal type theoretic exploration. For instance, Rust shows that it is possible to offer compile time checks for the third principle of isolation, even though it is not necessary for memory safety. This talk is near its end, so I would like to thank you for following it. I would also like to thank Leo White and Steven Dolan for freely sharing their thoughts and debating on this topic in the past years. Since I've got some time left, I would like to mention a couple of related works. The first one is the work by Aman and Bauer, who explain having recovered the distinction between checked and unchecked exceptions using algebraic considerations in denotational semantics, which constitutes a novel insight. In general, interpreting how semantic considerations relate to programming considerations as we developed here is hard work. For instance, a crucial question is whether the proposed finalization mechanisms are sufficiently expressive for programming at scale once the escape hatches have been taken away from the programmer. This is the main challenge in both of our approaches. Lastly, the debates about evolving exception handling models in programming languages is all the rage. For instance, with two recent proposals to evolve the error handling models of the C++ and C programming languages. I believe that being aware of the distinction and complementarity between the two methods of reasoning about exceptions can be helpful in the debates and controversies surrounding this topic beyond the OCaml and ML community. Thank you.